I'm Lee from BUPT, and this is a joint work with my advisor Shangguang and Mengwei. The title of this work is High-Density Mobile Cloud Gaming on Edge SoC Clusters. So let's start by the mobile games. Mobile games is a popular and portable form of entertainment on daily smartphones, and it has gained a huge and growing market. And there is an estimate of $100 billion USD revenue globally, and this value is estimated to be increased yearly. However, the better gaming experience calls for huge computation and storage resources. So these games to deliver immersive game views, and they also become more bigger and more complex, and they will potentially fully load the latest, even powerful mobile processor released in recent years. So these new resource-consuming mobile games may retire the old smartphones sooner or later. And there emerges mobile cloud gaming services to solve this question, to solve this problem. And they hold the mobile games in the cloud and transfer the games in to end users through the network. And through this approach, they can provide the end users instant access to any games with high compatibility, immersive game experience, and reduced hardware cost. In this work, we focus on the mobile cloud gaming infrastructure, as we've shown in the left figure. And this infrastructure is used to support the mobile cloud gaming services. So to support the services, the traditional approach is through the mobile environment emulation on Intel and ARM CPUs with server-level GPUs. Although the pros of this approach is that they can share the same hardware as other general workloads, it has several limitations. And the first is that there is performance loss incurred by the OS emulation. And second, this approach usually requires the game re-engineering to solve the compatibility and performance issues. And third is the limited game availability. Because some game developers, they may not want to provide the application package for other hardware platforms, like they don't want to provide the application package for the x86 platform to make them run on the Intel CPUs. So another approach we want to discuss in this work is the system on-chip clusters. And this cluster groups multiple mobile processors inside a server and provide identical mobile environments as on our user smartphones. Another benefit of this approach is the ease of deployment. And games are optimized for a single mobile processor, so the service operators can simply just put one game on one SoC. So with these benefits, what are the drawbacks of using SoC clusters? And by our observation, we find the primary drawback is that the low game deployment density. And this is mainly because the conservative game deployment methods. For example, the first and the most widely used is a dedicated game deployment, and they deploy one game instance per mobile SoC. And the second is game collocation, and they will collocate multiple game instances on the same mobile processor through pre-profiling to avoid any game performance drops. And we have evaluated the two methods on a single Qualcomm Snapdragon 865 SoC and report the hardware loss and game performance. And you can see in the figure, the results show that among the 5 evaluated games, 4 out of them can support only one game session per SoC, as collocating more instances will downgrade the game performance. When with one more game session, there are more than 50 CPU and 25 GPU resources are wasted because they can't accommodate one more game session. So when one more game session is co-located, and we can observe that the limited GPU capacity bottlenecks the game deployment density, and this motivates us to optimize the GPU resources on such SoC clusters. So the goal of this work is to run more mobile games within limited hardware resources of mobile SoCs. And this goal is similar to the goal of the traditional cloud gaming systems, right? But how well do the previous cloud gaming systems perform here? Because there are a lot of work before. And we conclude their approach as they usually split the complete game session, but in the cloud, they all consume a bunch of resources. And this is because they either run a full game copy on the cloud, or they will run a partial game instance in the cloud, which will still consume a lot of resources. And we will show this later. So to show their performance, we first revisit one game partitioning design that runs partial game session in the cloud. And this work was published at the Esplos 20 and named Coterie. And it splits the whole game world into a near part and a remote part according to a split distance, as you can see in the figure B and figure C. So the figure B and the figure C, the near part and the remote part, will run on different devices. And we selected one Unity-based game and 3 different distances to measure the GPU load of these 3 parts, and we can find that even the GPU load of the near part could decrease, but the remote part still only shows trivial or nearly 0 GPU load reduction. And we want to find why this happens. So in the last figure, at the figure C, and we can find the root cause is in the remote part, there are areas unnecessarily rendered, but will be occluded in the final game scene by the occlusion curling. And the occlusion curling is the graphics optimization by the graphics rendering pipeline. And this inspires us to conduct the occlusion curling process is conducted by the default graphics rendering pipeline, and we should preserve the optimizations brought by it. So we propose our system SFG, and our system employs a simple yet efficient partitioning method. And we want to partition the graphics rendering workloads before the rendering pipeline. And this is like the thought-first rendering in computer graphics. And we provide more flexibility, and we want to use one abstracted rectangle to represent the target area for rendering. And it also allows the runtime adjustment. And a demonstration figure is shown in the following. By default, in the left figure, the game camera can capture the whole game view. By replicating the main game camera, it can render a part of the scene with a user-defined area. And the second technique is the NPU-enhanced game partition coordination to handle the game usage dynamics. And here we make an assumption is we want the games to render their frames in native resolution. And even if there is no GPU resources left, we will involve the frame super resolution process to render a low resolution frame and to make the GPU to render a low resolution frame, and then use the frame resolution process to upscale it to the native resolution. With this assumption, our approach is divided into 2 stages. And in the first stage, we will deploy the partitioned game sessions with the well-deployed game sessions on 2 SoCs. And then we will shift the GPU rendering workloads through the coordination to make all game instances. On one of the SoC meet the performance target. And this process is invoked by a fixed interval. And the second stage is optional. And here we use one unique opportunity in SoC clusters is we observe that there are underutilized and idle SoC NPUs during the most game running. So if there are games on one of the SoC cluster, one of the SoC doesn't meet the performance target, and we apply the frame super resolution on it. So it's our evaluation section, and we implement our system as a Unity plugin that can be easily integrated into any Unity-based games. And we use the Unity's camera API for the game partitioning and use a WebRTC to transfer the game states and the rendering results. And for the frame super resolution, we use a quantized ETDS model and use the TF-Lite library to run it on the SoC NPUs. We also select 5 open source Unity games with varied graphic settings, including the resolution, FPS, and their different features like fast scene switch and slow scene switch. And we also simulate the gameplay by manually recording the interactive scripts powered by Unity's animation system. And these scripts will be played as a game runtime for deterministic interaction. For the hardware, we selected the SoC cluster consisting of 16 Qualcomm Snapdragon 865 SoCs, and each is equipped with the Android 10 OS. The network bandwidth between each SoC is 1 gigabits per second. So we first evaluate the effectiveness of the game partitioning design of the SFG, and we take the coterie, the distance-based partitioning the partition design proposed in coterie. And our partition design shows that it can reduce the GPU load by an average to 15%. But the most important is that it enables running the games on 2 SoCs that can't be supported on individual ones using the previous approaches. And the next is the end-to-end game deployment. And we select 3 baselines, and the dedicated deployment, the game collocation with the distance-based game partitioning, and the game collocation with our system. So the figure shows our result, and we can see that our method could support games exceeding the capacity of 1 SoC. So the 16 SoCs could support up to 13 games. And for the 3 games, we can find that our system could deliver up to 4.5 times improvement over the dedicated deployment in terms of the number of game sessions, and up to 1.5 times improvement over the previous collocation methods. And the next is whether our system will affect the FPS of these games. And the figure shows that it only involves trivial game performance reduction on one of the games, the Silver Mid, and its average FPS drops from the 54 to 52. And next is the hardware load. And from the figure, we can observe that the GPU load has an increase of 22% compared to the dedicated deployment, and the 7.5% increase compared to the game collocation strategies. And the average GPU load reaches up nearly to the full. And the additional CPU cost incurred by duplicating the game logic is manageable by a single SoC, as these games will cost less CPU resources. The last is the individual evaluation of the frame super resolution process. Because the frame super resolution is a complementary solution for the GPU shortage. And we found that in our end-to-end deployment, there are 4 out of all 5 games, and nearly 16% of all game sessions will involve the frame super resolution. And by measuring the latency, we can find that the frame super resolution process can be injected into the frame rendering process. And additionally, we want to highlight that the mobile NPUs are still fast growing, because Qualcomm has made a great effort to make current mobile NPUs to run more intensive workloads on their latest, like the Snapdragon 8 Gen 3 SoCs. And this improvement also brings more opportunities for us to our design. And to conclude, we first review the status quo of the mobile cloud gaming on SoC clusters. And we built the first system for high-density mobile cloud gaming on SoC clusters. And we use 2 simple yet efficient techniques. And the one is the pre-rendering game partitioning, and the NPU-enhanced game partitioning coordination mechanism. And our results show that there is improvement in game deployment density and their ability to support games that can't be supported by an individual SoC. And this also lengthens the life of current SoC clusters. And our code is open sourced as is linked. And thank you very much.